Yes, you can do the opening for now, and after that, I'm gonna open your slide and just start changing that.
Okay.
Now you can select all the things.
Okay, can I start now? Okay. I will start my presentation about some elements of fractional modeling with some restriction in time because the people are very hungry here. Also, the time schedule was a little bit changed as a result of the first lecture here. To everybody who knows me, I'm still alive, still working, and I will present some my idea. So, hi to everybody. What's that?
I'm gonna open your slide.
Okay, but
you can.
I like to present some practical steps about the construction of fractional model operators. You know now that there are a lot of articles of fractional order operators where practically all well-known models are transformed to fractional ones by simple replacement of the model. However, in the modeling, there is very, very strong rules that every model should satisfy some thermodynamic conditions. If you have some operators, local or no local, you can do what you like experiments, but you're creating the model, they should satisfy thermodynamic conditions because this is nature, and you can do nothing against the nature. This is my project that I work with different articles here, and the project why, how, and where. Why you should use a non-local modeling, how to implement the non-local operators, and where to apply the local operators here. The problems are different, but the rules are practically one and the same. Some basic notes at the beginning. There are several approaches to apply the non-local model. One approach is from the past, from the thermodynamics, when the people studied viscous elasticity, heat transfer with the finite speed, so the second sound. And this is the fading memory approach. This is and the second, the thermodynamic consistency of Volterra equation. This is older, very many about 16, 17. I try to present how the different kernel could be applied to order to obtain correct physical and mathematical models here. I will skip here because I already explained. There is a simple explanation how to apply mathematically this. For example, about the fractional calculus, there are two types of models. One is approximate model, where practically the model approximates to some way, and practically the Volterra approach and the fading memory approach are the same way. About the questional model, which is a little bit polite terminology, practically this is about the model with the replacement, because you have many questions. Why you did that? What is very important, there are too many principles in the modeling. This is a causality. I use causality in the Latin manner, not causality in English, because this is more easier to understand. Causality simple means, in the very domestic explanation, that you never have been born before your father. So there is a consequence of phenomena in this world. If there is in some material or some area, there is a disturbance is the first, and the reaction is the next. It's not possible to violate these rules here. Now, I saw that the fading memory formalism and both equations formally one and the same. The fading memory model formalism is based on the Boltzmann superposition principle, which is practically linear superposition principle. And they with it demonstrate how the transport models can be formulated in terms of memory, hereditary models here. What is causality? Causality is the first step that should be applied in any local and non-local model. For example, the classical Hooke mechanical law, you apply a force and then there is an extension of the spring, not there is no extension of the spring without application of the force. Who is the first? Who is the second? In the local model, where you have a fraction, Newton's second law, the force is proportional to the product of mass and acceleration here. But acceleration is a production of the applied force, so it should be a little bit in different manner. Okay, but every textbooks is rate of force is equal to mass of force. So this is a little bit pedagogical problem how to explain this. Causal material, this is a little bit philosophical. Causal efficiency, that the driving force and the driving step forward, there is a final state. There is no infinite position of here. And causa finale is that you should know what is the final result if you try to apply some disturbances of the setup. I will skip now this because you have no time. There is a primitive causality, and that the effect cannot precede the cause. That if the son cannot precede the father. The primitive causality is a very strong principle, and you have satisfied it in each model that I say. Now, because you are thinking about dynamical system here, we're changing in time. This is the general equation about any dynamic system. If you have a relationship between y and x, you are not interested about the real, but you are interested about their difference. Here, G, function of time, is a correlation function. In fractional calculus, you know, like a memory kernel. But you find the old study about the thermodynamics of fluids and that which are far away from the application of fractional calculus terminology, you can find this is the correlation function. The correlation function means that the closer events are more effective to the present than that in the past. For example, if you didn't sleep last week, you know what your behavior today. But if you sleep very well 1 week ago, there is no effect for your behavior today. This is the very simple domestic from the kitchen explanation. So in this explanation, practically you apply the general principle of primitive causality here. Now, what is the main result? I will skip here, constitutive modeling. Also, in addition, you should have a time frame indifference. This is a Galileo principle that the model should be one and the same, irrespective of the coordinate system that uses. This is on dependent coordinate system. Now I skip here now. You can see the same equation here, what is written about the viscous elasticity, that the stress is related to deformation, at this epsilon, to the correlation function R of sigma. Here, the lower terminal of integral is minus infinity, but this is a mathematical point of view because nothing happens in infinity if there is no process here. In fractional calculus and no local models, the zero is the beginning of the process. This is not a chronological time measured from the Gregorian calendar or Julian calendar as any others. If you start the process, this is the zero of the process, because in the real modeling, there is no infinite memory in minus infinity here. Now you can see this is a thermodynamic constraint, dissipation principle. Dissipation principle means that any model, local and non-local, the entropy should be positive. So you should generate. So what this means physically, if you do something, the process needs some maintenance. You should some minimal energy to support the process. And this is the entropy. You lost this energy without any benefits. This is support. This is practically the principle of entropy here. And here, you should, for example, for the simple diffusion model of heat, this is the condition that should be satisfied. In many articles, this is explained very well, because that I will skip this condition. What is that? The simple material. Simple materials with 62. Simple materials means that the flux of any materials is proportional to gradient. So you know from any textbooks what is the diffusion model of. This is the same, simple materials. If you have more complex materials, you should introduce more derivatives. But this is for the simple materials here. What is the fading memory constant? This means that after sometimes short time or long time, it depends on the process that you discuss. Here, the effect of the transition disappear. In Maxwell, in the 2 centuries about ago, discussed this problem with Fourier about the heat transfer here. What Maxwell thought, that transition of this process is very short, you should disappear. Because if you put the relaxation, you get the hyperbolic equation here. But if you neglect the relaxation because the material reacts very fast, you get the parabolic equations. Everybody knows from the mathematics that parabolic equations are not correct because they have an infinite speed of propagation here. If you try to model something real, you should put some in a way relaxation processes here. What is needed? This is the classical equation of fading memory. The first term M is what you reach after a long time, where practically there is no relaxation. The second term is the damping term. This is relaxation. And because of that, you have a finite speed of propagation. Because in this world, there is not something infinite. And there's something very big, something very small, but small and big and very large are qualitative explanation here. So after a long time, when the material or some structure accommodates itself, the second term disappear. In order to disappear in our models, M of sigma should vanish for a long time. This is the main condition of this correlation function here. So in the time of viscous elasticity, this is the strain relation time. What you do, you have a strip of caoutchouc, for example, is the rest. You try to extend it here. What is the pressure inside in the material? This is the deformation. Epsilon is the deformation. This is the relaxation function. Finally, you can see that you got the final relaxation according to the Hooke's law. What is the condition of the objectivity? In objectivity, this means the fading memory presented transfer processes. Now I can see what is the fading memory here. I'm skipping here. This is the heat flux here. This is the diffusion that you know from the Fick's law. This is the relaxation term in that. Now we are at the beginning to explain how from this general thermodynamics models, you can obtain fractional models here, because the problem is about the correlation function of the memory. Speaking in a little bit in the head, I saw if you can use relaxation kernel that you know from the fractional calculus, you are immediately obtain a fractional model here. So you can see the same that I explained it here, that the whole terminal of integral or the convolution should be zero because there is objectivity here. For example, in the viscous elasticity, deformation is a production of the forces that here, the tension, and the tension is production of a deformation. Here there are two correlation functions here. For example, if you have a strain here, there is a time, there is an increase, and this to some extent, to people who like to understand what is this resembles the Duhamel principle. In the Duhamel principle, you have a superposition of step, and that this is practically one and the same. If you have a simple conduction model and using the Cataneo principle, which practically the first who introduced the relaxation axle-dexter, you have this is the classical local model who have infinite speed here. But if you put this like a relaxation function here, that the flux is relaxing as a function of gradient here, and this is the relaxation, general relaxation function, correlation function that I use. Now, what is the interesting here? This is the delta function, Dirac delta function. That means if you use like a memory, there is no relaxation. If you have a here, there is a relaxation. If you try to apply this, you get the same. This is the general definition of the relaxation function. So the flux is this multiplied by this. You get the same principle here. Now I try to see how this principle can be applied to different memory kernels that you know. For example, if you have a Caputo derivative, if you have this is a general definition of the Caputo type derivative here, changing the memory, the exponential memory, you can get immediately in the Caputo-Fabrizio derivatives here. This is a little bit algorithmic approach. You have a template from thermodynamics here, and changing only that kernel, because the kernel depends on the physics, how the material, how the system is relaxing. For example, power law is from the physics. Exponential is also in the physics. If you open all books about the memory effects, everybody use exponential function. Nobody use power law. In fact, Mittag-Leffler function was used to model relaxation in viscous elasticity, and nobody thought something about against it. But when it introduced in the fractional operator, there is a big scandal in the society. So something exists in the nature, but some people don't like to understand that it should be used in different way. So if you have a Caputo-Fabrizio derivative, the final model is that you have a classical model, the first term, and damping term in this. If you have alpha 1, where practically means there is no relaxation function, you get the classical parabolic model. If you try to apply the same with the Mittag-Leffler function, with one parameter, you practically the same, we have the same algorithmic approach here. This can be found in the literature, and you get the same model here. What is interesting in this construction here, you have the same finite speed fractional modeling, but the time derivative, which usually replaced by fraction operator, is not touched. It's not touched. Because if you change the Frank derivative, you practically violate the first law of thermodynamics. This is the conservation. It's not. This is a balance equation here. The first law of thermodynamics means the time of t, for example, is proportional to the gradient, But if the gradient is relaxing, there is no need to put second relaxation here. There are some models where practically there are fractional derivatives here and both are equations here. But why you have a two competing relaxation function? Nobody answered that, but people only publish articles. They publish articles and solve. Nice calculation skills, but why? The problem is why here. For example, if we have a Parker kernel here, practically we have the same terminology because the problem is if your relaxation function, the fractional kernel corresponds to some problems that you try to model. The problem is one and the same. What the Parker kernel is that it's very difficult to find modeled system then can be modeled with that, because this is too complicated. If you have a kernel with too many parameters, okay, this is a generalization, but how you can control and how you can fit it to real system, because the problem will be imposed. There is a remark of the ABC operator here. Here, you know it, it's a Tangana-Baleano. This is a special case of the kernel that somebody tried to introduce that. If you do that, you can define a new operator, because every term that you receive like a relaxation, you can be defined like a new operator. But the problem is just how to use. So my advice is don't use in wrong way, not way. If you have a Botnov kernel that everybody is interested in everything, you can construct the same. So, for example, there is a Young derivative that was introduced without any motivation, but this existed in the literature. You can see that you can get the same. If you have a Volterra approach, now I can see. Okay. If you have a Volterra approach, which is practically one and the same, this is the Volterra approach. You have this and integral of that. If you here introduce a kernel of memory, you practically get one and the same. Now I will be a little bit fast because the people are hungry. And so I'm not so beautiful to be watched all the time. Here you get practically the same type of equation. So the method that I present a little bit algorithmic and that I discussed to Professor Jeremy, maybe one day it will be incorporated in ChatGPT to create directly articles with that. But you have the same algorithmic here you can get it because as a construction Volterra approach and fading memory approach practically one and the same. If we have a Parker kernel and the memory, we get the same equation. Because the difference between the parabolic equation and the Volterra equation is only the additional memory term that you use. So this is from Justy, who told that everything with Fabrizio and Tangana-Baleano is wrong, and only Parker is the correct. So this is the bottom of this one the same. For example, presentation on with the similar content is available in the website ResearchGate. So everybody who would like to study step by step, you can see that. There are too many articles. What is the remark, this is a final remark, that all examples, when we apply the water approach here, for example, naturally lead to damping term in the Riemann-Liouville equation, but equations are hyperbolic, the second order. If you replace the time derivative in the energy balance, the first law that I saw by replacement, you practically violate the thermodynamic conditions. So you can do a very good academic career, but you don't do nothing here. So there is a strong interrelationship between the memory formalism and Volterra that I already said. This is practically involving the same construction of the model here. And final comments. So I saw what I know or what I think about how you can control. So far, after my publication, nobody said that this is wrong. This is thermodynamically correct. Maybe somebody who solved too many equations with replacement, I'm not satisfied. But I think that somebody who starts now to work will be satisfied, because you cannot do nothing against the God. That's inshallah. So thank you very much for my for the attention. Here, if there are any questions, sure, because the lunch is waiting. But in the lobby, I can discuss with everybody what you need.
Something, please.
Huh?
Would you allow me to just?
Okay.
I'm very sorry being late to this session because we had another presentation in the other section. And so the duration of the speech was extended. That's why I was late. I could not introduce you to the auditors, so audience. So let me introduce you and then we can give you.
So, what I'm a
I'm very
professor.
sorry. Pardon me, please.
Okay, introduce me.
Yeah. I'll introduce you. The people already knows you.
I will help you.
Okay. No, I just get some knowledge. I wanted to talk about that one. It's very interesting.
Okay.
Professor Jordan Hristov is
Hristov, this is the Christopher in the Western Mother.
Chemical engineering. He's from University of Chemical Technology and Metallurgy in Sofia. He's our neighbor, very close to Istanbul. So he has quite large expertise in some fields. Let me tell you about that. You may just ask him questions about these topics. Numerical simulation, mathematical modeling, fluid mechanics, computational fluid dynamics, engineering thermodynamics, thermal engineering, modeling and simulation, modeling, numerical modeling and numerical analysis. You see how large.
No, some of this content is generated by ChatGPT, because I don't work on numerical modelings and that.
I really get it from the ChatGPT.
I was graduated as electrical engineer in measurement, and step by step I grew to the full professor of chemical engineering, mainly on modeling and mechanical process. There is no chemistry there. There is a process there.
So thank you very much.
Thank you to you also. I will add some conditions, some additional information. So I'm working now. I'm emeritus, working very hard. Less lecture, more science. So I'm happy. And next week I will be 71. So I like to be 81 in the next meeting with you.
Yeah. Hopefully.
I think that in 10 years I will be still active, but inshallah.
Inshallah.
Okay, thank you very much for your attention. And that's all.
We would like to take Professor Dr. Hristov for any live presentation.
Okay.
As Professor Dr. Kontay'dan continuing this session. Professor Dr. Kontay'dan to present a plate of appreciation to our distinguished speaker, Professor Dr. Jordan Hristov.
For the memory propaganda.
Yeah. Don't remember.
propaganda of the conference. I don't like all the officials, but
Dear participants, we have now reached the lunch break. Lunch will be served in dining hall located on the ground floor. The lunch break will take place until 13:15. We invite you to join us there and wish you an enjoyable meal. After the break, our program will continue at schedule at main hall.
I like, but just apply it